We were looking at this question related to discrete random variables, where in part A, B, and C, we mainly looked at how we can find expected value and variance of our discrete random variable. Now, in part D, we will focus on how we can find expected value and variance of a linear function of a random variable. So, part D tells us the project cost is made up of two parts. So cost is made up of a fixed cost of 20,000. So it's this part here, a fixed cost of 20,000 plus 2,000 for each day taken to complete the project. So plus 2,000x, where if you recall from part 1, x is the number of days it takes to complete the project. So the first step is that we write this function for cost, where we know there's a fixed cost of 20,000 plus 2,000 times the number of days it takes to complete the project, because because for each day it's 2,000, so you just multiply the number of days it takes to complete with 2,000. Now let's find expected value of cost. So expected value of cost is essentially expected value of this function that we just wrote, 20,000 plus 2,000x. Now, using the property, now here we'll use the property of expectations. Using the property of expectations that expected value of ax plus b, where a and b are constants, is a expected value of x plus b. We're going to use this property where expectation can go inside summation, which means that expectation of sum is sum of expectations. Expectation of constant is equal to the constant, and constant multiples can come outside of expectation. So if we use this property and apply it here, so this would be expected value of cost. So we know, so we can just write this 20,000 as is, because it will become expected value of 20,000 plus expected value of 2,000x. And we know expectation of a constant is the constant, like over here, the b that comes here. So it's like the way we treated this b over here. So this 20,000 is treated in the same way. Plus, we know constants can come outside expectation, so it's 2,000, just like this a came out over here. So this 2,000 is treated in the same way into expected value of x. So here we just simply apply this property, expected value of ax plus b, where a is just simply, in this case, 2,000. So it just comes out like this, and b is just simply 20,000. So this is 20,000, right? So we just applied this property of expectation here to find the expected value of this linear function of this random variable x. Now we know, since expected value of x is 3.2. We found this in part B in part 1 of this video. So expected value of cost is equal to 20,000 plus, so we know what expected value of x is. Let's just plug this in 3.2. So this is going to be turned out to be $26,400 is expected value of cost. Now we want to do the same thing, and now I want to find the variance. So let's just delete this. Right, so sorry, we want to find the standard deviation of cost, but before that, I will first find variance, because then you can find standard deviation is just square root of variance. So let's first find variance of the cost. So we just want to find variance for this, right? So, okay, so now let's do that. So we have variance of cost is equal to essentially variance of this function, 20,000 plus 2,000x. Now here again we use a property, just like you had a property for expectation, we have a property for variance for ax plus b. Using property of variance, that variance, just like you had a property for expected value for x plus b, we'll write for variance ax plus b. It's just a squared variance of x, right? So then what happens, so we are using property of variance, that variance of ax plus b is equal to a square variance of x. We can write variance of cost. Here we can notice that this is essentially RB and this is essentially RA. So this will just become a square, which is 2,000 square into variance of x, right? We just applied this property. Since variance of x is equal to 1.06, we found this in part C, in part 1 of this video from part C. So variance of cost is equal to 2000 square into variance of x, which is 1.06, is just 4241234. So we know standard deviation of cost. We know standard deviation is always square root of variance, is square root of variance of cost, right? So it's square root of this. So it's square root of 4241234. So it's 2059.126 is your standard deviation of cost. So now the last part is sorry. So the last part is where if three projects are undertaken. So now we want to talk about that. If three projects are undertaken, what is the probability that at least two of them will take at least four sorry, let me just flip a highlighter. Um hmm, will take at least 4 days to complete, assuming independence of individual projects completion time. Okay, so here we're interested in finding the number of projects that will take at least 4 days to complete. We want to find the probability that there will be at least two such projects. So let's define a new random variable. The first random variable x we defined was the number of days to take to complete the project. Now we'll define let y. So the first random variable was x, right, which is the number of days it takes to complete a project. Now y be the random variable that denotes, because this is what you're interested in finding now, the probability that there'll be two such projects. That denotes the number of projects that will take at least 4 days to complete. That will take at least 4 days to complete. Right? So we want to find the number of projects. Because over here we want to find the probability that at least two of them will take at least 4 days to complete, right? So we're defining a new random variable which is denoting the number of projects that will take at least 4 days to complete. Now what we should note here is that y is a binomial random variable. Y is binomial random variable where you have three projects, right? N the number which in this case represents the number of projects is 3, and the probability of success we'll just find that. But let's first look at why can we even apply binomial. Remember, binomial has some conditions where you need finite independent trials and constant probability of success in each trial. So in this case, we know there are finite number of projects, which in this case are just 4. Sorry, these are 3. And independence, they've told us over here, assuming independence of individual project completion time. So this takes part of the independence condition to apply binomial. The third is you need a constant probability of success. So for each project, the probability of success will be constant. What will be the probability of success? The probability of success over here, like in this case, the probability, remember success is in terms of whatever we're looking for. Here success is the probability, so this is the probability of success, probability that a project takes at least 4 days to complete. So here we've defined success to be, success is always in terms of whatever you're looking for. Here our success is that the project takes at least 4 days to complete. Right? A project takes at least 4 days to complete. Right? This is success here in this context, depending on what we want to find. So this is success here, right? So we essentially want to find the probability that x is greater than equal to 4, right? Because if we recall, x represents the number of days it takes to complete a project. Right? So we want to find the probability number of days it takes to complete a project denoted by x is greater than equal to 4. So this is the probability x is 4 or x is 5, because if we recall, we defined x to be, because remember x takes values 1, 2, 3, 4, 5. So the probability that x is greater than equal to 4 can be 4 or 5, because remember we talked about the values that x can take go from 1 to 5. That's why it's important to keep in mind the values a discrete random variable takes. And we know, okay, or means union. So this is the probability x is 4 union x is 5. And because these are mutual, the random variable taking different values is mutually exclusive events. So we can So we know in the case of mutually exclusive events, the probability of the union is the sum of their probabilities since mutually exclusive. So just keep this in mind. The only way we can write probability of union is sum of probabilities in the case of mutually exclusive events. Otherwise, we can't. Otherwise, it's like probability A union B is probability of A plus probability of B minus probability intersection. Right here, we don't have to worry about that because they're mutually exclusive. So we can just add the individual probabilities. So probability x is 4 is 0.3. We can see it from there. And probability x is 5 is 0.1 is 0.4. So we found that the probability of success is 0.4. So now we've established it's a binomial random variable where we know it's going to take values 0, 1, 2, 3 because binomial random variable takes values from 0 to n. Because if you have n trials, so the possible successes that you can have is 0 to n because there's a possibility that all trials can be a failure, some can be failure, some can be success, or all can be success. So this indicates that none of the projects meet this condition. This shows that all the projects meet this condition. 1 and 2 is some 2 and some 2, right? All of these are possibilities. And again, it's helpful to keep in mind the values the discrete random variable takes when finding the probabilities. So the first thing to identify over here was that we need to create a new variable, and it is going to be a binomial random variable. It meets all three conditions which we need to be careful about. You have finite trials, you have independent trials. Independence is by assumption, and you have constant probability of success, where we just found the probability of success. Now that we know, so let's just quickly write this again. Then we can do the question. So y is binomial. Write the number of trials in this case, which represents the number of projects, is 3. Probability of success is 0.4. And y takes value 0, 1, 2, and 3. This is important to keep in mind. So now we want to find the probability that there are at least two projects that will take at least 4 days to complete, right? So the probability that there are at least two projects, so probability y is greater than equal to 2 because at least means greater than equal to, right? At least 2, right? At least means greater than equal to, right? Probability at least 2, right? So now the probability that y is greater than equal to 2, so we know that y can take values from 0 to 3. So the probability that y is at least 2 means the probability y is 2 or y. See, that is why again it's important to keep in mind the values a discrete random variable takes, because if I'm saying the probability y is at least 2, so we know this binomial random variable only takes values 0 to 3. So this is a probability that it's either 2 or it's 3. So or means union, like we said. Again, the same logic applies here, that you can write this as probability y is equal to 2 union y is equal to 3. And we know, so we can, we can further write this as probability y is 2 plus probability y is, because whenever you have a random variable, the random variable taking on different values are mutually exclusive events, right? Because the random variable, once you do an experiment, once an experiment is done, only takes one possible value. Like at one time, it can only take one value. So these are mutually exclusive. So the probability of the union is the sum of the individual probabilities. So this is just going to be now, to find this, we need to recall what the PMF of a binomial random variable is like. Oh, wait, let me just do this. Right, so let's recall here, before we do it, recall. So recall PMF of a binomial random variable, if we just say y, because here we named our binomial random variable y, is probability y is equal to k, right? We know this is n choose k, pk 1 minus p. This is just the PMF of a binomial random variable. In this case, we know n is 3 and p is 0.4. So the probability that y is equal to any value k is just 3 choose k, 0.4 power k, 1 minus 0.4 is 0.6, 3 minus k, right? Now we just need to, instead of k, first plug in y is 2, right? So probability y is 2 would just be 3 choose 2. So I'm just using this over here and plugging in instead of k2, right? So we're just using this. The PMF in this particular case with this particular n and this particular p. So 3 choose 2, 0.4 power 2, 0.6 power 3 minus 2, which is 1. Now probability y is 3, so instead of k, I'll just plug in 3. So plus 3 choose 3, 0.4 power 3, 0.6 power 0. And this turns out to be 0.352.